Okay, so it's starting to record. Okay, so I think we can start. Okay, so it's a pleasure for me to introduce today Professor Michael Kinyon from the University of Denver. And if I remember correctly, he is also somewhat connected to Portugal because he's adjunct professor at the Open University of Portugal and a full member of the Center for Experimental and Stochastic Mathematics of the University of Lisbon. I hope I didn't forget anything. And
That's okay. Some of those things are no longer.
that's good.
No
Okay,
longer
perfect. I
active.
just searched
Doesn't
for,
matter.
but it's okay. And he's an expert in quasi groups, loops, semi-groups, and monoid. I think those are still in the process. And in fact, he will speak about the structureless Cheban loops, which is some of his stronghold. And also, I think he will try to sensibilize us about the problem of humanizing proofs generated by computers, or maybe not to humanizing proofs generated. Who knows? He will tell us. So please, Michael, the floor is yours. Thank you.
Well, thank you very much. And also, good morning. Uh, it's 9 a.m. here in Denver, and I understand it's middle of the afternoon there. Uh, but I'm ready, as you can see. So, um, what I would like to talk to you today about, whoops, sorry, there we go. Um, is some joint work that I've been doing with Alish Drapal, and this is on a particular class of loops. And after thinking about it for a while, I realized that one of the problems with this talk is that, in some sense, the class of loops that I'm going to talk about is so obscure that it's probably not going to be a lot of interest to people other than loop theorists, even people in non-associative algebra. So I'm going to actually try to make the theme of the talk a little bit different than just talking about the structure of left Cheban loops, and I'll explain what those are pretty soon here. Um, so let's first of all, just a reminder of where we all live. Uh, so this is MSc classification 20, and starting with the most general on the top and the most specific on the bottom. And when I give talks about this to associative mathematicians, of course, they're all very comfortable with the left side of this picture, but not so much the right side. So this is what we're going to do is discuss the right-hand side of this picture. And specifically, we're going to be talking about loops. I'm not going to really say anything about quasi-groups in general in this talk. So let me give you a little bit of background to what the problem is that Alesh and I were working on. So first of all, we should start, as always, with the definition of what a loop is. Now imagine that you were actually hearing a group theory talk by a distinguished group theorist or someone like that, and they've started the talk with the definition of a group. You would think that was a little strange, right? Uh, because everybody knows what that is. But it's still traditional, despite how long loop theory has been around, to start with the definition. So here it is. A loop is a set with a binary operation such that for each pair of elements in the set, certain equations can be uniquely solved. Okay, so the existence of these solutions is just simply part of one of the axioms. And there's also an identity element. So the first part just says it's a quasi-group, and the second part says that there is an identity element. And one can, of course, use the definition of that you can actually use associative loop as being a definition of group if you want to. But we, of course, are interested in non-associative loops. So let's talk about those. Now, the multiplication table of a finite loop is exactly the same thing as a reduced Latin square. So remember that a Latin square is reduced if the first row and the first column have been, well, the square has been arranged in such a way that the first row and the first column correspond to an identity element. So they just duplicate the things on the border. So here is a Latin square of order 7, and without mentally calculating any instances of associativity. So don't look at the elements and try to calculate associativity. Uh, I hope you can see after staring at it for a couple of moments that this is not a group. Now, if this were a live audience, I would probably call on somebody to to point this out. But I will just give you a spoiler and show it to you right away. The issue is look in the upper left-hand corner. Here is a subloop of order 3, namely the set 1, 2, 3. But on the other hand, this particular loop has order 7. If it were associative, then it would violate Lagrange's theorem. So it can't possibly be associative. So now, how do we study loops? Probably the most famous class of loops, non-associative loops, are Moufang loops. And I think a lot of people in this audience are well aware of this because you know that in an alternative algebras satisfy the Moufang identities. And so once you make sense of what it means to have an invertible element in an alternative algebra, you know that under multiplication, these will form a loop, and namely a Moufang loop. And some of the best known examples of loops are the ones associated with the octonions of Moufang loops. So, for example, the non-zero octonions under multiplication form a Moufang loop. I haven't actually defined what a Moufang loop is. I'm just giving you some, I'll do that shortly, but I'm just giving you some examples. The seven-dimensional sphere is closed under octonion multiplication and forms a very nice subloop. There's also such a thing as the octonion loop, as it's called. This is analogous to the quaternion group of order 8. The octonion loop is just the signed basis elements of the octonions, and that's also closed under multiplication. And there are many, many other subloops. And here's a very fuzzy picture, and I wish it were better, of Ruth Moufang herself. Now, there's one other class, which is not quite as famous as Moufang loops, but is still rather ubiquitous in terms of how much it occurs in mathematics outside of just the non-associative world. And these are what are called Boole loops, named after Garrett Ball, um, who is pictured here, I think when he was visiting Princeton. Um, a couple of examples. I didn't actually write down the operation for the first example because it's messy and would take up a whole screen. But if you look at the set of relativistic velocity vectors under Einstein's velocity addition law, um, and I'm talking here about the law in general, where you are allowing yourself to add together under the law non-parallel velocities. This is not associative, and it turns out to be what's called a Boole loop. And another example is the set of real n by n positive definite symmetric matrices under a strange looking operation, which is actually related to the polar decomposition for n by n matrices. Okay. So those are probably the two classes of loops that are, in some sense, pervade the most outside of the world of just non-associative structures. I'm not saying those are the only two. There certainly are others, but these are the two examples I want to focus on. Now, how are they defined? Actually, I gave you the examples first without telling you what they are. Well, Moufang loops are usually defined by identities. There are three identities, and they turn out to all be equivalent in loops. So you can pick any one of them and use it as the definition of what a Moufang loop is. And there's a similar identity for Boole loops, or strictly speaking, left Boole loops, or right Boole loops are with the order of everything turned the other way around. And these are identities that generalize associativity. And you will notice that they have certain features in common. So, in fact, for example, the Boole identity there is very similar to the first Moufang identity. And in fact, just to add to the confusion, those of you who are familiar with those of you in non-associative algebra who are familiar with alternative algebras and Jordan algebras and so on, what loop theorists call the Boole identity, many people in other parts of non-associative algebra call the left Moufang identity, which is, from a loop theory perspective, is a little bit confusing. Um, Now they all these identities have a couple of things in common. They have three variables. One of the variables is repeated, and on both sides of the identity, the variables occur in the same order. Okay. Um, so uh, Back in 1969, Ferenc Fenyvich decided that that might be an interesting way to try to look at some classification of loops. If you're going to try to think about how you're going to study all loops, you have to come up with some sort of scheme for doing it. You can try to just, study the general theory of loops, but and you can do that, but then you'll rapidly hit a wall because there are so many different types of loops. So Finyavish's idea was let's try to classify loops on the basis of the identities that they satisfy. And based on the two examples that I've already given you, he called an identity. He said an identity has Boole-Moufang type if it has the same properties I was just describing to you. So all three variables occur on both sides in the same order, and one of the variables occurs twice. Okay. Now, if you count how many of such things there are, so you first figure out how you can arrange the order in which you're going to arrange the variables, and then you figure out how to parenthesize them. Okay, and then you discard any duplicate identities that you might have come up with in the meantime. Then it turns out that there are 60 identities of Boole-Moufang type. And what Fenyvich managed to do by hand and with a lot of patience is to sort out what the corresponding loop varieties are. And when I say variety, I mean in the universal algebra sense of variety, not the algebraic geometry sense. Finyavish's classification had a few minor gaps, but these were fixed in 2005 by J.D. Phillips and Petr Wojciechowski, who made use of technology. Namely, they used the automated theorem prover, Prover 9, and the finite model builder, Mace 4, to distinguish some of the cases that Finyavich was not able to distinguish. Um, and Okay, so I mentioned that there are 60 identities of Boole-Moufang type. It turns out that 30 of them are equivalent to associativity. Um, so for example, here's one, for example, that's equivalent to associativity, and you can see that just by canceling the X that's on the right. Remember, we're in the loop world, so you can always cancel. Um, some of them turn out to be equivalent identities in just two variables. So for example, here's one which looks like it's a three variable identity, but it's actually just the flexible law. And in the end, once you sort everything out, the 60 reduced to 14. There are just 14 distinct varieties of loops of Boole-Moufang type. And some of them we already know. There are groups, there are Moufang loops, there are Boole loops, and then there are a few others which we're not going to go into for the purposes of this talk. Um, at at the time he wrote this paper in 1969, some of the varieties that he introduced were new and had never been considered. In the many decades that have elapsed since then, some of them, oh well, all of them have been studied in one form or another. Okay, now let's get to Cheban. Excuse me, I'm sorry. Um, so in a pair of papers that he wrote well, the first one in 1976, and then the follow-up was 4 years later, Cheban considered a generalization of loops of Boole-Moufang type. Now, when I say that, that's a little bit unfair to him because from what I can tell, he wasn't aware of Finyavish's work. He was just starting over from scratch. But this time he allowed the variables to occur in a different order on both sides of the identity. And of course, this explodes the number of possibilities. Well, no, I don't mean dramatically explodes, but it certainly increases it quite a bit. And nowadays we call these identities of generalized Moufang type. Cheban just said of length 4 and rank 3, where length is how many variables occur on one side, and the rank is the number of variables. And here are 3 examples of such things that are of generalized Moufang type, but not of Moufang type, because the order in which the variables occur has been rearranged. Now, Cheban did not attempt an exhaustive study of these things. And given the resources he was working with, that's hardly surprising, because if you count them, there are 1,215 such identities. So in 2011, a group of undergraduate students at Northern Michigan University used Prover9 and Mace4 to sort all of these things into the distinct loop varieties. And what they found is that the 1,215 collapsed down to 48. So there are the 14 varieties I already mentioned of Moufang type. Then there are 6 varieties which are Moufang type but commutative. And then there are 28 others. You can think of them as being exceptional, but just consider them as being new varieties. Now, all of those varieties have since then, that was 2011, all of them have been described with varying degrees of thoroughness. And it turns out that most of them are subvarieties of very well studied classes. So they can be easily characterized. And then the only hard part is just seeing if you can construct examples. And by the way, that's always the hard part in loop theory, is seeing if you can find examples of some phenomenon. There are too many cases where in loop theory where you're studying some particular class of loops and you have no idea if if you're studying anything that doesn't already exist under some other name. Now, the varieties that Cheban himself studied certainly turned out to be the most interesting in this class of 28 new varieties of loops. And they were actually the ones I showed you just a couple of slides ago. Here they are again. And this time I've put little labels on them. And because Cheban thought that they were important, we call these the left Cheban, right Cheban, and middle, although we usually drop the word middle, Cheban identities respectively. Now, if you look at the first and the second one, the left and the right ones, you notice that the right-hand side of the identities is the same. And therefore, if you set the left sides equal to each other, you get the third identity. And that shows you that left Cheban plus right Cheban implies the one without a prefix, so the one without the left-right consideration, just Cheban. And it turns out the other way around is also true. If you start with a Cheban loop, then it implies the 2 one-sided versions of it. In his original paper, the second paper, the 1980 paper, Cheban constructed a non-Moufang loop satisfying the first identity. That was really one of his 2 goals in that paper. And the way he did it is he constructed a 7-dimensional associative algebra over Z2, and then he took the direct product of 4 copies of it, and he built a new multiplication on top of that. So if you just count elements instead of thinking about dimensions, his loop is rather large. It has order 2 to the 28th. Oops, sorry. There we go. Now, in 2010, J.D. Phillips and Victor Shcherbacov published a short paper on both left Cheban and Cheban loops. If you're going to study the left-handed case, you don't have to study the right-handed case because everything is just dualizes. And they used the automated theorem prover, Prover9 again, but they just made the conscious decision not to humanize most of the proofs. So most of the paper just consists of a theorem statement and then referencing their personal archive of the proofs, which the link is, by the way, in their paper no longer works, but if you want to see their original versions of their proofs, you can request it from J.D. Phillips. On the other hand, they're also not that hard to reproduce. So one result is the one I already mentioned, which is that a loop is Cheban if and only if it's both left and right. And I should mention in fairness that Cheban was probably aware of this, but his paper is worded kind of strangely, and so he doesn't actually say it explicitly. Now, interesting thing here, Cheban's original 1980 paper was only 4 pages long. And the Phillips and Shcherbacov paper was only 5 pages long. So from 1980 until now, so in the 46 years, only 9 pages have been published about these loops. So if we tacitly assume that studying these loops is not a vacuous activity, in other words, we're not just talking about the trivial loop or some other class, Alesh and I decided to pick this up and push it in a couple of different directions. And by the way, the assumption that this was a reasonable thing to do turned out to be correct because there are examples. First is to try to actually find human proofs of all the results in the Phillips-Shcherbacov paper. Now that by itself is probably not publishable except in some minor journal because it's just one could just sit down, look at computer output, and just go through line by line and try to understand, write down the equations that are being proved. But here, when we say human proof, we were hoping to find conceptual proofs. That is, proofs that, while yes, you may have to do some ugly calculations every once in a while, still the overall theme of the proof is conceptual. And then we decided if we could push things beyond what Phillips and Shcherbacov did, especially for left Cheban loops, because most of their strong results were about the two-sided case, the Cheban loops. So that's as far as that's what we decided to do, and that's the bit of the history here. So let me give you a brief crash course in loop theory so I can describe some of the results. I'm not going to actually be proving anything at all in this talk, in the fine tradition of talks nowadays. Okay, so first of all, if you're in a loop, remember that because they're quasi-groups, they're defined by certain equations having unique solutions. So what we do is we will introduce some notation for those unique solutions, namely using a backslash and a forward slash to represent left and right division. You know what that already what that means in groups or even in Moufang loops and other classes as well. Those operations can be expressed in terms of multiplication and inverses, but in general loops they cannot be. And these are characterized by certain equations holding. So for example, in the 2 lines there showing the equations in A and B, the left-hand equations say that multiplication on one side or the other is injective, and on the other side, the right-hand equations say it's surjective. And the point of view that is taken is that it's actually better to think of loops or quasi-groups in general as having 3 binary operations, not just one. They should have a multiplication and 2 divisions. Now, besides being nicer from a universal algebra point of view, this point of view also has computational advantages. It's much easier to compute with loops, especially in automated theorem provers, if you think of them as having 3 operations, not just one. So just to show you what things look like if you're using automated deduction, here's a fragment of a Prover 9 input file for left Cheban loops. So the first part is loop axioms, and you can see that they are just, I did this in a fixed width font because this is sort of the default. And you can see that each of the statements is followed by a period. I've collapsed them onto the same line so that it fits on the slide. And it's quite readable, right? And there's the left Cheban identity, which we saw earlier. And there is a tacit assumption here that all these things are universally quantified. Okay, that's hidden in the background. You don't have to say for all x, for all y, for all z. Now there are other automated theorem provers that you may have heard of, like Vampire and some other ones, and they all work just fine too. The only difference is they use a somewhat more cryptic input language, which I didn't want to show you because then I would spend most of the time just explaining what it was you were looking at. Now, conceptually, a lot of the ideas from group theory, or what's better is to think about it as universal algebra, will transfer very easily to loops. So it's pretty clear what a subloop should be. It's clear what a homomorphism should be. It should preserve all three operations. Normal subloops that, well, these would just be kernels of homomorphisms, okay? Or if you want, they would be the congruence class containing the identity element for a congruence in the universal algebra sense of congruence, and quotients and so on. And if you sort of think about what these concepts should mean based on your experience with group theory, then you're exactly right, that they mean precisely what you think they should mean. Now, there are other notions which are a little more specific to loop theory. And so let's, for example, look at the notion of a center. So the center of a group, which, as you know, is traditionally denoted with a Z or a Z, is the set of elements that commute with everything. And if you're thinking about what the center of a loop should be, you might guess that that's what it would be, okay? But that's actually not the correct definition of center. And when I say not correct, I mean, it's a definition. How could it be wrong? Well, it doesn't lead anywhere. For example, that definition gives you a set that's almost never a subloop. I mean, it is in certain special circumstances, but not in general. And even when it is a subloop, it usually isn't a normal subloop, which is another thing that you would want. And one of the recurring themes that one notices when you start studying loops is that if you're in the absence of associativity, commutativity is actually not that strong a property. So here's what the right definition of a center is. To tell you that, I have to introduce a notion which is very familiar to people in non-associative algebra, other parts of it, which is the nuclei. So this is defined the same way it's defined for other non-associative algebras, and we use the same terminology. We call them nuclei. So there's a left one, a middle one, and a right one, and these are just the sets of elements that associate with all other elements in that particular position, left, middle, or right. And then when you take the intersection of all of these things, that's just called the nucleus without any word coming in front of it. Now, these always are subloops. They are not necessarily normal, but that's okay because it turns out that in the cases of interest today, they are normal. Well, a couple of them are normal. So here's going back to the center, for instance. The center of a loop is the set of all elements that both commute and associate with all other elements. So it's the subset of the nucleus consisting of elements that commute with, everything in the loop. And this is always a normal subloop. So just to go back to coding, for example, if you're interested in that side of things, here's how you would tell prover 9 that some fixed element C, uppercase C, is in the center of a loop. You would just simply write down the fact that it commutes with everything, and then write down that it's in each of the three nuclei. And that's it. And the variables there, the lowercase letters, are all universally quantified. C is a constant. Okay. Now, so let's talk about commutators and associators, because that's going to come up here in the encoding issue. So the traditional, one of the two traditional definitions of a commutator in group theory is X inverse Y inverse XY. The other convention, of course, moves the inverses on the other side. In loop theory, one of the conventional definitions of commutator just mimics this. It's yx divided into xy. And we also have associators. Now, this doesn't look the same as what associators mean to a non-associative algebraist, because if you're working, for example, in alternative algebras or Jordan algebras or whatever, um, an associator is defined using the additive structure as well as the multiplicative structure. Here we don't have that to work with. So what we do is we just write the two ways of associating x, y, z, and then we divide one of them by the other. And by convention, this just happens. We just use the left division. It doesn't really matter that much. Okay. Check the time. Okay, we're doing okay. So for example, here's how you might define commutators and associators in Prover 9. I used K because K is the first letter in the word commutator, of course, and A for associator. Okay. And so let's say, let's talk about nilpotence. One of the reasons I'm talking about that is because that's related to one of the results for Cheban loops. So how is nilpotence defined? Well, let's go back to thinking about group theory for a minute. In a typical group theory course, a student's first encounter with nilpotence is usually in terms of either the upper central series or the lower central series, one or the other. Now here's the version in terms of the upper central series, right? This is very familiar. You have this sequence of characteristic subgroups, which goes up to the top group in finitely many steps. And each one of this is just the pre-image of the center of a quotient. And of course, a beginning student who barely understands what a quotient is probably very stuck at this point. But then you find out later that nilpotency can actually be expressed equationally. So let's say that you wanted to tell, for example, an automated theorem prover that a group is nilpotent of class at most 3. Well, here's how you would do it. You just iterate the commutator, okay, a couple of times, or 3 times, in fact. And this, I know from experience that students actually like this a lot better. Okay, so here's how you would do this for loops. So nilpotency of loops, you can define it in terms of upper central series and lower central series, and the definition just goes through without change. Okay, if you want to actually encode this in a first order way, so that you are doing equational calculations, here's what it would look like. It's just 8 equations, and all these things say is that commutators and associators commute and associate with everything. In other words, the center contains all commutators and all associators. And that's all those things say. There's a lot of variables there, but once you conceptualize it, you can see exactly what it means. Okay. Now, so much for that. Let's go back to left Cheban loops and Cheban loops themselves, using some of the loop theory that we just discussed. Now, one useful gadget are the translations, which people in non-associative algebra are certainly familiar with. The idea going back, for example, to A. Albert, that you should think about non-associative algebras in terms of their corresponding multiplication algebras. So you have for a given loop, you have left translations and right translations. And here I have my mappings acting on the left of their arguments. And these are, by definition of what a loop is, these are actually bijections, or if you prefer, you can think of them as permutations. And together they generate what's called the multiplication group of a loop. So for example, if you have a group in the first place, and then you look at the group generated by the left and right translations, that's just 2 copies of the group, but then you have to mod out the center, a copy of the center. Now, in general, you can study loops through their multiplication groups. We're not doing that here because it doesn't really help. And also multiplication groups don't necessarily completely determine a loop. For example, the quaternion and dihedral groups of order 8 have the same multiplication group. Okay, now when we're doing calculations by hand, we often will work in terms of the translations, the L's and the R's, instead of in terms of loop words with the multiplication and the backslash and the forward slash. And the reason for this, there are a couple of reasons for this, but the main one is that when we're doing hand calculations, it's nicer to calculate in a group. In the doing calculations with translations in the multiplication group is easier because function composition is associative. So for example, here is the left Cheban identity in its original loop form again, and there is the translation form. So you think of the x's and y's as acting on z, okay, and you can write it in that particular form. Now let's rearrange that a little bit, and let's replace x with x under y and simplify it. And what we get is the equation here at the bottom of the screen. And notice what this says. This says that if you conjugate one left translation by another one, you get another left translation. So in other words, this says the set of all left translations is closed under self-conjugation. Now those are called, surprise, surprise, left conjugacy closed loops. So left Cheban loops are a subclass of left conjugacy closed loops. There are more left conjugacy closed loops than just those. And that actually already says a lot about their structure because left conjugacy closed loops have been very thoroughly studied in the past, I want to say about the past 3 decades. In fact, even longer. So for example, the left and the middle nuclei coincide, as it turns out, in such loops. And in the case of a Cheban loop, which is both left and right Cheban, that means that they are both left conjugacy closed and right conjugacy closed, which means exactly what you think it should mean. The right translations are closed under conjugation. And even more is known about such loops. So not only is the nucleus itself normal, but it's known that the quotient by the nucleus is actually an abelian group. And in the case of Cheban loops, this was essentially Cheban's second main result. The first one being the construction of a loop of order 2 to the 28th that I mentioned earlier. Now, I remind you, his paper was only 4 pages long, so the proofs are a little bit sketchy. But he didn't have the whole theory of left conjugacy closed and right conjugacy closed loops to fall back on. So he proved this directly using just the Cheban structure. Here's another observation. Here's the left Cheban identity yet again. And now take z equal to 1. Okay? And you notice what it says. It says that xxy is yxx, but parenthesized in a particular way. Now, we didn't know what to really call this property, so we just call it symmetric squaring. It's not a very good name, but we don't have a better idea. I should mention for those of you who are used to alternative algebras, you probably think that this says something about squares commuting with everything. But neither left Cheban loops nor Cheban loops have to be alternative. I mean, they can be, in which case they belong to a subclass. But they don't, in general, they don't have to be. So this property is just as it is. And that's actually a characterization. A left Cheban loop is precisely an LCC loop with this symmetric squaring property, as it turns out. So the main result that Phillips and Shcherbacov showed about Cheban loops is actually the following. In addition to some other structural features that I won't go into because they would only interest loop theorists, they showed that Cheban loops are actually all nilpotent of class at most 2. Non-Moufang examples do exist, and they're quite a bit smaller than than the stuff that Cheban was constructing. The smallest examples have order 16. in fact. And it turns out that order 16 is small enough that this is something easily doable by computation, and then you can verify later that it actually does what it's supposed to do. Now, I mentioned to you that one of our original goals was to try to find human proofs of most of the Phillips-Shcherbacov results. And sometimes just knowing what the statement of a theorem is enough to give you an idea how to prove it, right? And that's actually the case for most of the results in the Phillips-Shcherbacov paper. In advance, we wouldn't have known what the results were, but once we knew what they were, then we were able to find human proofs without having to humanize the prover 9 output, which was, in most cases, was quite beneficial. Now, it would turn out, sometimes I would check later, it would turn out that our human proof was actually very similar to the automated proof. And that's not surprising. Sometimes you're proving something where there just are not that many ways to prove it. And that was the case for some of these results. In the case of this nilpotence result, for example, it doesn't follow the prover 9 proof at all. It just uses structural theory based on other classes of loops that have been studied in the meantime since Cheban wrote his original paper. Now, there was one exception to what I just said, which is this result of Phillips and Shcherbacov, which is that the quotient of a left Cheban loop by its center has exponent dividing 4. I should say that, by the way, since everybody here in this audience knows what power associativity means, that Cheban loops and left Cheban loops and so on are all power associative, as it turns out. So exponent dividing 4 makes perfect sense. This was actually the most difficult case because this one required actually reading the prover 9 output and trying to look at conceptual issues. Okay, but as I also mentioned, just trying to find human proofs of somebody else's automated theorem proving results isn't intrinsically all that interesting. We wanted to find some new stuff, and we did. So to start with, we decided we better generate some examples of left Cheban loops that are not Cheban loops, and that would give us some hints as to what the possible theorems might be. And we were able to find some. The smallest examples have order 32, and there are, in fact, up to isomorphism, there are 4 of them. And they all turn out to be nilpotent of class 3, exactly 3. And in all 4 of them, the quotient by the left nucleus is an abelian group of exponent 2. Now, we were able to prove from that, this led us to a conjecture about Cheban loops, namely that any left Cheban loop of class less than 3 is Cheban. And we were able to prove this. It turns out not to be that complicated. What I'd like to do is focus on the third bullet point there, which is the quotient by the left nucleus is an abelian group of exponent 2, because we were able to get a proof of this. This was actually hard to do. There are many people who don't use automated theorem provers get the impression that they behave like black boxes. You put in an input file, you start them up, you go away, you grab a cup of coffee like this, and you let the program run for a long time, maybe a couple of centuries, because after all, you have no idea when it's going to finish or find anything. And that's it, okay? Well, that's rarely what happens. First of all, if you let an automated theorem prover run for a long time, it will eventually consume all of your memory and resources. And so it'll just crash. And it doesn't matter how good it is, it'll still do that anyway. But more to the point, the whole process of proving something with an automated theorem prover is really an interactive process. I'm not saying these are interactive theorem provers. They're not. They're not like Lean or Agda or some of the other ones. You are encoding something in a first order way, like we did with nilpotence, for example, and trying to see what happens there. But when you have some experience, and especially when you have expertise in your subject area, you can tell when a search is going well or when it's going badly. Um, so the proof that I just mentioned, the theorem that I just mentioned, we have not humanized the proof. And there's a very simple reason for it. I have several different copies of the proof, meaning, well, not copies of the same proof, but variant proofs that I've obtained by changing parameters and changing input a little bit and things like that. But they are all of them thousands of steps long. Okay. I think the shortest one that I have is about 6,000 steps long. And when I say steps, I'm referring to equational inferences. So where you take one side of an equation and you plug it in as a subterm of another side, and then you draw consequences from that. So if you're reasonably comfortable asserting that computer-assisted proofs are really proofs, we can be sure that this is a theorem, and I'm okay with that. That's reason, you can in principle at least verify these things. But the problem is that prover 9 and other automated theorem provers are first order theorem provers. We've already seen that from how I was encoding nilpotents. And that means that the proofs for equational problems are just equation bashing. You take equations and you smash them into each other and you get new equations and so on. And there's absolutely nothing conceptual about that. It's just pure computational nonsense. Okay. Now, this is different from the sort of computer-aided proofs that have been making the news lately, namely using Lean or AGDA, and also in conjunction with large language models. Now, there, the emphasis in those provers is on formalization, but proofs given by automated theorem provers are formal by default because they're just formal as output. Now, the informal parts, the human parts of the current proofs that we do have would not be very hard to formalize if you were using a system that had a reasonably good loop theory library. None of them do, surprise, surprise. I mean, loop theory isn't exactly mainstream. But none of that anyway, the point is that none of that really helps us understand the main parts of this proof that I just was talking about. Now, sometimes when you're reading output, if your eyes don't completely glaze over, the output will suggest conceptualized proofs. You might read an equation, and because you're an expert, you immediately recognize what the equation means. Okay, so for example, if you're doing group theory and you see a commutator embedded in a commutator equals 1, you immediately know what that means. It means you have a group that's nilpotent of class at most 2. So here's the problem. Freud once said a cigar is just a cigar sometimes. And that's the problem here. Sometimes an equational proof is just an equational proof. There's no conceptual issues behind it. And all you can basically do is just clean it up a little bit to make it readable for a human. Readable in the sense of not so many coding issues. And I have to say that having done this for 20-something years, both extremes where you have conceptual insights and just pure equation bashing happen a lot, even in the same project. So if a proof is several thousand steps long, there is no way I or anyone else is going to humanize it. Okay, I mean, I have better things to do with my time. And even if I did start to humanize it, I don't know in advance that there's anything conceptual to look at in there. There could be maybe some small parts, but I don't know that. And maybe most of it is just equation bashing, and that's the best I can do. So the law of diminishing returns, and this is an example of that law, says just leave it alone. And so for the time being, until we come up with a better idea, we're just going to leave it alone. Now, finally, you might ask if a large language model like Claude or ChatGPT or any of the other ones that have been in the mathematical news lately can help with humanization of proofs coming from automated theorem provers. That is, could I just feed the proof to Claude or to ChatGPT and say, please come up with a human proof of this? Well, as they're currently configured, the answer is no. I mean, mostly because just as an experiment, I've tried it, at least with the free versions of these things. And the problem is that they don't have They haven't been trained on this kind of stuff. So they don't really know what it means when they're looking at the output. Am I saying it couldn't be done? No, it probably could be. It would take a lot of patience and quite a bit of training to do it. And I have to confess, at the moment, I'm not very motivated to do it. Besides the ethical concerns about using these sorts of things, I just don't want to put the time in. Anyway, I'm going to stop there. I really appreciate your patience with me and your attention. So thanks very much indeed.
Thank you for the nice and very instructive talk. Okay. Are there any questions or comments for Michael?
Should I stop sharing?
Oh, yeah, if you wish, but maybe some questions may refer to the slides.
Oh, yeah, good point. Good point.
I cannot see any from the participants. Well, meanwhile, I think I have a question about it's just a curiosity actually about because I'm group theorist actually, so it's always nice when you speak about center and something similar. So it's very exciting to generalize things. And so there is a nice, beautiful theorem in group theory which says that if the center is very large, I mean it's a finite index, the index is bounded by some constant something, then you can also bound the derived subgroup, which is the sure theorem. Oh,
You can also bound what subgroup? I didn't hear
the
that.
derived subgroup.
Oh,
So
the
if,
derived subgroup.
if
Yes.
the index of the center is small in some sense, also the derived subgroup as order bound and so on. And I was wondering if there is something similar that one can say for loops or something with the new I mean definition of center.
That's a very interesting question. I will say that in general, these sorts of the sorts of theorems that you're alluding to, where you have you have some sort of finite index condition on maybe a subgroup or something like that, and you then draw conclusions about the original group. I have to say that no one has really looked at this. And if you ask things about like virtual properties, for example, and things like that, um, uh, it would not surprise me if such things were true. But as far as I know, most of this, or asymptotic loop theory, you might consider, for example, most of this has been untouched. And I think it's primarily just because of the size of the field. There are not that many people who who do this. So it's a great question, but unfortunately, the answer is we don't know.
We do not have many more people dealing with this. Yes, there is
Yeah,
not
yeah,
enough people dealing with that. Okay, well, it's fine.
that's true.
Well, maybe after this talk, some other will join. Hopefully. Okay, let me see if there is any other question, but I don't see any other question. If I'm mistaken for some reason, please step in and say you are wrong. There is a question, but otherwise, we should thank again Michael Kinyon. And I think the meeting should stop now, and we will meet again next Monday. Okay. Bye.
Okay.
Good morning, and have a nice day.
Thank you. Bye-bye.
Thank you. Bye-bye.